Hello and welcome to ASTM E74-18 Explained. My name is Henry Zumbrun, President of Morehouse Instrument Company. If you have any questions at or during this webinar, please feel free to contact me at either 717-843-0081 or hzumbrun@mhforce.com. I would be happy to answer any questions that may come up. A little bit about Morehouse. We are a manufacturing company that produces force calibration equipment and adapters that are used in industry to measure force. We have a state-of-the-art force and torque calibration laboratories and offer calibrations at a very high level of accuracy. Our force capability, we offer deadweight primary standard calibrations accurate to 0.002% of applied force up to 120,000, that's 20 parts per million. Other force calibrations are offered up to 2.25 million or 10 meganewton, known to within 0.01%. Morehouse Torque Calibration Laboratory features primary torque calibration standard accurate to 0.0025% of applied torque. This standard was commissioned by NPL, who is an NMI in the United Kingdom. The standard is the second most accurate torque standard in the world. Today's webinar will be covering ASTM E74 Explained. There will be a brief summary on measurement uncertainty. We will cover primary standards and secondary standards as defined by this standard. We will cover the ASTM E74-18 calibration procedure. First, to understand some things, we want to understand some measurement-related terms. Metrological traceability, which is the property of a measurement result whereby the result can be related to a reference through a documented, unbroken chain of calibrations, each contributing to the measurement uncertainty. What's important here is a reference can be a definition of a measurement unit through its practical realization. Metrological traceability requires an established calibration hierarchy. So what that's essentially saying is we start with one level, and as we go down, every time we get further and further away from that, what's in force calibration, the primary standard, the larger the uncertainty is going to become. So we start typically at primary standards, K equal 2 values from 10 parts to 50 parts per million. These are tier 1 is primary standards. It's dead weight applied without intervening mechanisms such as levers, hydraulic multipliers, or the like, whose mass has been determined by comparison with reference standards traceable to national standards of mass. And force weights require the correction for the effects of local gravity and air buoyancy. Tier 2 would be your secondary standards. Those are the standards that are calibrated by primary standards such as load cells, proving rings, and other force measuring devices or mechanisms like your lever machines and everything else. The calibration of which has been established by comparison with primary standards. And typically uncertainties in this range, or CMCs, around 01 to 05. And then the third tier are like the working standards, devices such as load cells, force gauges, crane scales, dynamometers. Where the laboratory falls into this range largely depends on the reference standard used to calibrate the device. That's basically saying I need a really good reference standard, typically to calibrate to 0.1%. But if I have my reference standards not too good, maybe 05, it may be more difficult to get 0.1. So it's really saying you need to compare do the proper uncertainty formulas and figure out what type of reference standards you need to get the accuracy requirement or uncertainty requirements you need. And then we have tier 4, which devices for force verification instruments or universal testing machines, UTMs, used for testing material or verification of forces. Further dissemination of force is uncommon after this tier's measurement uncertainty becomes quite large. So calculating force CMCs. CMCs are calibration and measurement capabilities. The guidance documents that are currently out there are NCSLI RP12, determining and reporting measurement uncertainties. There's really a lack of proper guidance document for non-ASTM E74 cals. With the E74 stuff, you can use a combination of the appendix with A2LA R205, specific requirements is pretty good foundational piece. And then for the ISO 376 calibrations, if you're doing cal in accordance with 7500 or doing a CMC analysis to ISO 376, Euromit CG4 is an excellent document. We currently have a draft of an uncertainty document that was given to A2LA. It's on its third revision, and I hope to be published by the end of the year. So if we're doing calibration in accordance with ASTM E74, and we're going to figure out our calibration measurement capability, we're going to have some type A uncertainty contributors. And the biggest one is going to be the ASTM lower limit factor. This is going to be reported on the ASTM calibration report, and we're going to reduce this to one standard deviation. The LLF is usually reported with a K coverage factor of 2.4. Then the other type A components, repeatability of a best existing device. This is where we want the best load cell, best proving ring, best instrument, the most stable device with the best resolution, because we're going to want this to do a repeatability study. And then we're going to do repeatability and reproducibility between technicians over a period of time. There are lots of ways to do these. They're broken down differently. We have an Excel document that helps the type, and then we look at type B contributors, and those are such contributors: resolution of the best existing device, reference standard resolution, that's if applicable. If you're using dead weight, fortunate enough to have primary standards, you're not going to have reference standards resolution, reference standard uncertainty, reference standard stability, environmental factors, and then you have other error sources, which is a catch-all. The important thing here is do not use SEB, nonlinearity, or hysteresis, as they are not appropriate contributors when following the ASTM E74 standard. So if we're going to do a CMC or measurement capability, we would need the calibration report for the device. Here's a sample of that. Lower limit factors are here. The uncertainty of the instruments that were used to perform the calibration, that's you reference. Calibration history, where compare one calibration versus the next. You're going to use the drift specification. You're going to compare one cal versus the next, compare the drift or the stability. Manufacturer specification sheet, we're basically going to use this for the most part for environmental if the temperature varies from the temperature at the lab it was calibrated at. Other error sources if known, and then the end user, you get all that back. You'll have to do repeatability study, R&R, usually between technicians, and as a requirement, if you're accredited, you're going to have to complete proficiency testing requirements. Morehouse has simplified this. We have an Excel sheet I mentioned earlier for anyone needing to calculate measurement uncertainty. It can be downloaded here. The measurement uncertainty sheet, you fill in everything. There's red tabs that guide you through everything, fill in everything, and it will give you a report at the end, which will give you the coefficients for your uncertainty. This particular one was for our PCM, and at PCM at 10%, we're at 02234, and at capacity, the 2,000-pound portable calibrating machine, we were at 00551. Typical uncertainties for the PCM will vary depending on everything that's testing. Anywhere from 0.3 to 0.5% is typically achievable throughout the loading range down through the 10% point. This one was very good. Sometimes we get a little worse. So measurement uncertainty, the measurement hierarchy, everything's traceable back to SI. If we're looking at the uncertainty propagation, it's from SI, and then we have NMIs, National Metrology Institutes. In this country, NIST has force capability of 4 parts per million. NIST calibrated the Morehouse weights that we're using in our machine. Our machine is known to within 8 parts per million for standard uncertainty. Typical accredited cal suppliers are around 0.2. You may see them better than that. You may see them a little worse than that. Working standards typically 0.01, and then field measurement 0.5%. So you can see how the uncertainty becomes larger the further away from SI units or the further away from primary standards. If we examine the CMC Morehouse versus an accredited cal supplier, you can see our expanded uncertainty. This is a 10,000-pound load cell. If we do the calibration, we get our CMC at 10,000 pounds is 0.16. We tested this cell and the repeatability was 0.057%. You can see the stability. We put everything possible in this machine. in this calibration using our deadweight machine. And then when we went over and did the same thing in a secondary transfer machine, and the expanded uncertainty of that, we started at around 0.4. If done in the secondary, transfer machine with load cells, the expanded uncertainty of that 10K load cell was about 4.03 pounds. So accredited cal supplier, we actually did the test on one of our hydraulic frames, not a Morehouse machine, another type of hydraulic machine that's sold by our competitors that we have, and we got a repeatability of 0.379. So we did this test simulating what secondary standards would people would typically be using versus deadweight primary standards. And the expanded uncertainty when calibrated with primary standards was approximately 10 times lower than using secondary standards. So if you're a critical application, you want the lowest uncertainty, deadweight is the best. If we look at the test uncertainty ratios, Morehouse versus a typical force calibration lab, TUR is tolerance divided by expanded uncertainty, where expanded uncertainty is the CMC, this formula over here. If we look at this, we took a 10,000 pound device, we set an accuracy spec of 0.05%. That happens to correlate with ASTM class AA device, what the expectation would be, with a 0.01 pound resolution and 0.1 pound repeatability. The Morehouse CMC 002 of applied, tolerance 10 pounds, expanded uncertainty 0.24. That would give us a TUR of 21:1. Here's our setup. This is from our lab, or it's actually in our torque lab, and it's a setup of one of these machines that most of our competitors sell that does tension compression. The same setup with all these control cell right here, reference cell right here in this cell. So we did the same cal with a 10,000 pound device, as I said earlier. If we were to use this machine, 10,000 pound accurate to 0.5%, exact same things, tolerance of 10 pounds. The expanded uncertainty of this machine now is around 5 pounds. The TUR would be 1:1. So TUR, Morehouse versus typical force calibration lab. The graph on the left is Morehouse. To the right and to the left of the nominal value, very, very small curve, where the typical force lab is going to have a larger curve. What this does is the larger that normal distribution curve, the more risk on the laboratory. So if we have 10,000 pounds and the instrument reads 10,000 pounds when 10,000 is applied, these are the graphs. If we shift the location of the measurement to 10,004, what do you think happens? Well, if we shift the 10,004, Morehouse, can still say the device is in tolerance. Most people think the device is still in tolerance in general if the upper specification and lower specification is plus or minus 5 pounds. But when we calibrated, it is. When the lab with a CMC of 0.5% calibrates it, the risk goes from 4.66 to 30.47. So it's important to look at this, the actual location of the measurement here and the width of the curve. So in this scenario, the lab within the CMC of 0.5 calibrates this device, and they record it read 10,004. The actual risk to the person using it, there's a 34.47% chance that the device is actually intolerant or out of tolerance when the lab is saying it is in tolerance. So essentially, what I like to say Morehouse does, Morehouse lowers measurement risk for force and torque measuring instruments. The lab with the smaller uncertainties will produce larger TURs, giving you more space to be in tolerance. In this scenario, look at all the room to the right and the left. More room. I use a car scenario. If you have more room to be in tolerance, you can open up your car door as wide as possible, get out, and not have to shimmy or squeeze or suck something in to shimmy through, or dent the car beside you or have your car dented. Measurement uncertainty. Here's an example where the expanded uncertainty is less than the reference standard uncertainty. This is another calibration supplier certificate. It should never happen. There they say the estimated measurement uncertainty is 5.5 pounds, but they're saying the ASTM uncertainty they're basically saying this is completely wrong. They're saying the ASTM uncertainty represents an expanded uncertainty with a 99.5% 99% coverage factor, and it's wrong. And then we get into using the right calibration suppliers. So anybody that's looking for a calibration supplier and they want ASTM E74 or they want ISO 376, they want class AA, they should look at someone's scope of accreditation. And if they want decremental loading, a decreasing to determine hysteresis or some other things, they should look at the scope and make sure the lab that's performing the calibration has a low enough CMC to say the device is in tolerance or not, and that they can meet what is requested. The actual role of Morehouse in the measurement hierarchy, we typically calibrate the secondary or working standards that are then used to calibrate other force instrumentation or testing machines. Almost every item is tested. The ASTM E74 standard is used to calibrate secondary standards that are used to calibrate testing machines in accordance with ASTM E4-18. Some examples include testing the ripeness of apples. You know, if you're going to ship something, if you're a West Coast manufacturer and you want to ship something to the East, you're going to want to ship the harder apples because they can mature longer and they have more time to ripen. The softer apples you're going to want to ship locally because you don't have that much time before they go bad. Figure 11 there's testing the strength of coffee packaging. There's fishing line, testing the adhesive peeling forces of foil packaging, testing the crushing strength of pills, determining the force to remove the lid from a plastic package. So, and then we get to the actual ASTM E74-18 standard and start with its primary force standard, which is defined as a deadweight force applied directly without intervening mechanisms such as levers, hydraulic multipliers, or the like, whose mass has been determined by comparison with reference standards traceable to national standards of mass. To be classified as a primary standard, the masses of weights shall be determined within 0.005% of their values by comparison with reference standards traceable to International System of Units, SI for maths, and this is in ASTM E74 section 6.1.2. Primary standards require correction for the effects of local gravity, air buoyancy. Again, they must be adjusted to 50 parts per million or better. NIST weights are adjusted to within 5 parts or better, and Morehouse weights are adjusted to within 20 parts or better. For ASTM E74-18, section 6.1, weights shall be made of rolled, forged, or cast metal. Adjustment cavities should be closed by threaded plugs or suitable seals. External surfaces of weights shall have a roughness average of 3.2 microinches or less as specified by ASME B46.1, and stainless steel is preferred. Secondary force standard is defined by ASTM E74, which is an instrument or mechanism the calibration of which has been established by comparison with primary standards. In order to perform calibrations in accordance with ASTM E74, your force standard must be calibrated with primary standards. Some examples of secondary standards in machine: here's a 100,000-pound load cell. We calibrated that in our dead weight machine. Couldn't assign a class AA range. We can calibrate all kinds of instrumentation. If we wanted to, we could calibrate this dynamometer to ASTM E74 and assign a class A loading range because we have a AA device. We will talk more about that later. We have a 10,000-pound bench top here where we're calibrating AP dynamometer, and then we have our 2,000-pound PCM where we have a load cell set up as the standard and we're calibrating a handheld force gauge. So secondary force standard as defined by E74, the range of use is limited by the verified range of forces. This is a terminology change between ASTM E74-13 and 18. This used to be called the loading range, and this you'll now hear ASTM referring things to that loading range, the old loading range, as the verified range of forces. ASTM E74 class AA verified range of forces for calibration of secondary standard load cell. Basically, this is found by multiplying the lower limit factor LLF by 2000, which gives us the 0.05% or a 5-to-1 ratio. ASTM class A verified range of forces for calibration of testing machine. This is found by multiplying the lower limit factor by 400. 4-to-1 ratio. It's important here at the end. Range of use cannot be less than the lowest applied force. Loading range cannot be less than 400 times 400 times the lower limit factor for Class A, or 2,000 times the lower limit factor for Class AA, or times the resolution. So test the way ASTM works. So you have a test accuracy ratio with primary standards. Those need to be better than 50 parts per million. They're required to calibrate secondary standards. Primary standards can be used to calibrate working standards, as this will often result in the lowest possible loading ranges. So we have a primary standard here at the top of the pyramid. We can calibrate secondary standards. We can calibrate working standards. Probably not going to be able to calibrate the testing machine, but theoretically we could if we carried our dead weights on site, but that rarely happens. And then secondary standards are required to calibrate working standards. They cannot calibrate other secondary standards, and working standards are used to calibrate the testing machine. So as you can see here, the TAR, the test accuracy ratio starts, we're getting a 10-to-1 between primary and secondary, and then between secondary and working, we have a 5-to-1. And then between the testing machine, we have the 4-to-1. If any of this is broken, if someone does not follow this, meaning they used working standard to calibrate another working standard, this pyramid or this TAR breaks, and ASTM becomes essentially useless if you break this confined TAR ratio. So we get into the actual calibration, the preparation. The first thing we're going to want to stabilize the device. It's a recommended device be kept in the lab area or where it's going to be calibrated for at least 24 hours. If it's a real large load cell, like a 800 pound, 1 million pound capacity load cell, you may need longer than 24 hours. The recommended temperature is 23 degrees. Electrical stabilization, depending on the equipment, common practice is to allow 15 to 30 minutes to warm up. We typically, around like 15-20 minutes, we typically start exercising, and then it's about 30 minutes until we actually start the calibration. Exercise the instrument to be calibrated. The instrument should be set up in the machine and exercised to a maximum force that is to be applied during the actual calibration. Typically, we recommend 3 to 4 exercise cycles. Most standards require a minimum of 2 exercise cycles. You're going to know when by the zero return on a load cell. Most load cells respond very well to 3, some need 4. The procedure, at least 30 force applications are required. We typically recommend 3 runs of 11 or 33 force applications. There should be at least 1 calibration force for each 10% interval throughout the loading range. And if the instrument is to be used below 10% of capacity, a low force should be applied. Hence, that is why we recommend 11, because we're recommending a force be applied below 10%. It's usually 400 times the resolution, 2,000 times the resolution, or 2%. Whatever of all of those is the greatest. This low force must be greater than the resolution of the device multiplied by 400 for Class A or 2,000 for Class AA. The reason ASTM uses 30 points is the rate of change in the standard error approaches 0 at about 30 samples. This is why 30 samples is often recommended when generating summary statistics such as the mean and standard deviation. This is also at the point where the T and Z distributions become nearly equivalent. So we're out here at 30. It's really where we have minimal error. If we go 33, 34, it's not going to gain that much. In fact, around 24, somewhere in there, ISO 376 requires at least 24. And around 24, you can still do fairly well between comparing standard error and sample size. But in any case, ASTM requires 30, and it is because it reduces that standard error. Calibration temperature. ASTM E74 requires that the temperature be monitored during calibration as close to the device as possible, and the temperature change shall not exceed plus or minus 1 degree C during calibration. Temperature corrections must be applied to non-compensated devices. Deflection generally increases by 0.027% for each degree C increase in temperature. If the calibration laboratory is not operating at 23 degrees C, they should make the corrections by correcting the applied force accordingly. Randomization of loading conditions. This is new. This is a major change in ASTM E74-18. It was not a note that was moved up or anything else. It is completely rewritten. They used to allow 2 runs of 15 for 30 points and some other things. In this new section 751 and 2, basically says in compression, tension calibration, position the force measuring instrument to a 0-degree reference position and then rotate to positions of approximately 120 degrees and 240 degrees. An exception is made for force measurings that cannot be rotated by 120 degrees, such as proving rings, force dynamometers, and Brunel hardness testers. For these types of force measuring instruments, position the force measuring instrument at 0 degrees, then rotate to positions of approximately 60 and 300 degrees, keeping the force axis on center force axis of the machine. This exception is made to minimize parallax errors. If you're reading a device, it's hard to rotate it 120 degrees if you have to look at it. So as a committee, we worked on this for probably a good year and a half to get this wording and everything right. There were lots of arguments about using mirrors and doing other things, but in the end, it came down to that everybody agreed 120 to 0, 120, 240 for digital devices. If you have to be in front of it and you have to see it, it's going to be very hard to go to that 120 and 240, so 60 and 300 degrees. Randomization of loading conditions for tension and compression calibration. Intersperse the loadings. Be sure to re-exercise the force measuring instrument prior to any change in setup. 0 return during calibration. This is lab dependent and is recommended that no more than 5 forces be applied before return to 0. We typically recommend even odd. Even though it's recommended that no more than 5, a 6 and 5 is fine. And it depends on the machine. It depends on the conditions. If you're doing a load cell calibration where you can hit all the points nominally, your weight stack is such that you can hit 1,000 pounds, 2, 3, 4, 200 pounds, and 1,000, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sometimes we're going to do a whole cow without returning to 0, and it just depends on knowing the instrument and knowing the equipment and the best method to really give the most repeatable results and the expected performance of that device to characterize that device. So deflection calculation methods, we have 2 methods. We used to only have 1. Method B is readings should be calculated as the difference between readings at the applied force and the average or interpolated 0 force readings before and after the applied readings. Basically, method B is your standard. You have 1 0 that you start with, and you have an ending 0, and then decide if you're going to do average or interpolated 0 force readings. And then you have method A. Because people in the field, they said we're ignoring the trailing zeros for the class A type devices or for calibration of testing machines, they came up with this method A, which method A deflection readings are calculated as the difference between the deflection at the applied force and the initial 0 force. What's important about method A, 99% of our customers are using method B. Right here, it's pretty standard in most industry. Method A, if elected, requires an additional test. It requires a creep test, which only needs to be done at the beginning of the life of the load cell, unless the load cell has shifted or changed. So if you are using method A, you need to have that creep test certificate. Decreasing loading. If the load cell is to be used to make descending measurements, it must be calibrated with a descending range. We did this. We took a 100K load cell and compared to 50, around the 50% points, and I got -203040 on the ascending curve versus -203126. So the descending curves here in orange, and when we came back, you can see in the blue curve there was a difference. The additional error was about 0.042%. If you're calibrating a device to ASTM class AA, the allowable is around 0.05% at the first point. So this is approaching the allowable maximum. It's not right to use an ascending curve to make descending measurements, and hence ASTM moved a note that gave guidance to actual requirement in section 7.4.1, which basically states force measuring instruments are usually used under increasing forces, but if a force measuring instrument is to be used under decreasing force, it shall. The note said should, and now it says it shall be calibrated under decreasing forces as well as under increasing forces. Use the procedures for calibration and analysis data given in section 7 and 8, except where otherwise noted. When a force measuring instrument is calibrated with both increasing and decreasing forces, the same force value should be applied for the increasing and decreasing directions of force application, but separate calibration equations should be developed. So if it's used to make descending measurements, it needs to be calibrated in that manner. Separate calibration curves can be used for ascending values and descending values. A combined curve may also be used, though the standard deviation of combined curve will be much higher than using separate curves. So what do we mean by that? So if we use a combined curve, we're going to take the values, the ascending values, and we're going to combine them with the descending values. And by doing so, any measurements made within these combined value should fall within the expected performance, should fall within the lower limit factor. If we're doing, we typically recommend to use an ascending curve only for the ascending measurements and use a combined curve for the ascending and descending measurements, unless you're fully going to capacity. So they set a separate descending curve, but the only way the descending curve is valid is if you go right here to capacity and then come back down. If you're only going to 50%, you're going to get a much different value. If you can see my pen there, your curve's not going to, it's going to be a much, where I shaded in all that yellow there, it's going to be a much different value than if you go to capacity. So that's why we recommend a combined curve if you don't want to get the instrument certified at 50%, 30%, do load loops or do anything else. It's a lot easier maybe to do a combined curve. Criteria for higher degree curve fits. ASTM allows up to a 5th degree. To go higher than a 2nd degree, the resolution must exceed 50,000 counts. An F distribution test is used to determine the appropriate best degree of fit. Instructions for this test can be found at the Annex A1 of the ASTM E74 standard. And this is a change. It's from a should to a shall be used in the ASTM E74-18. It used to say should be used, and now it's, if you look at the new verbiage, it says it shall. So you shall use an F distribution test. And then the standard deviation for established curve fit is calculated as before, using all the individual deflection values, which we will go over. So criteria for lower load limit. It's lower LLF, lower limit factor is 2.4 times the standard deviation, which corresponds to roughly 98.2 confidence level. This was made in the 70s. It was not changed. They've used 2.4 since the standard was adopted in 1974. It's based on the lower limit factor or resolution, whichever is higher. Class A, 400 times the lower limit factor or resolution, or 400 times the resolution, whichever's higher. Class AA, 2,000 times the lower limit factor or resolution, whichever is higher. Any force measuring instrument that is either modified or repaired should be recalibrated. Recalibration is required for permanent zero shift exceeding 1% of full scale. And then we get to calibration intervals. We talked a little bit about uncertainty and stability. Well, looking at section 11.2.1, force measuring instruments shall demonstrate changes in the calibration values over the range of use during the recalibration interval of less than 0.032% of reading for force measuring instruments and systems used over the Class A verified range of forces, and less than 0.16% of reading for those instruments and systems used over the Class A verified range of forces. Force measuring instruments not meeting the stability criteria of 11.2.1 shall be recalibrated at intervals that shall ensure the stability criteria are not exceeded during the recalibration interval. So what does this mean? If it meets, it can go to a 2-year interval. If it doesn't meet, the end user is responsible to verify to ensure that it does meet. So you set the calibration interval for 18 months. If it doesn't meet, it has to be shorter than 18 months. If you set it for a year and it doesn't meet, then maybe you're going to go every 9 months until it meets. If it doesn't meet at 9 months, it has to go to 6 months, and so on and so on. Really, if the device is not that stable, it should be replaced. If you're not getting at least a year or more out of it, it should be replaced. ASTM calibration. The Class A or AA verified range of forces cannot be less than the first applied non-zero force point. So let's look at this. This is a older cert. You can see 2006. It's not to the ASTM 18 standard, but the same thing. This applies in both. So we have a lower limit factor of 0.132, but yet we have a Class A loading range of 200 to 10,000 pounds. Why is that? If we take 400 times 0.132, we get 52.8. Well, our first non-zero force point that we did was 200 pounds. So per section 8.6.2 of ASTM E74-18, the verified range of forces shall not include forces outside the range of forces applied during the calibration. If the lower force limit is less than the lowest non-zero calibration force applied, then the lower force limit of the verified range of forces is equal to the lowest calibration force applied. So there's lowest calibration force, 200, could be lower. That's the first point we did. Recommendation, ASTM is recommended the lower force limit be not less than 2%, 150 of the capacity of the instrument. That's still a recommendation. It's people request, customers request 1%. We're glad to do it if it meets resolution times 400 or resolution times 2000 criteria. The other section, people say, well, hey, 0 can be my first force point. I can just put a 0 there and then I can claim the 52 pounds. But no, per section 7.2.1, if the lower force limit of the verified range of force measuring instrument is anticipated to be less than 1/10 of the maximum force applied during calibration, then forces should be applied at or below this lower force limit. In no case should the smallest force be applied be below the lower force limit of the force measuring instrument as defined by the values 400 times resolution for class A, verified range of forces, 2000 for class AA, verified range of forces. So guess what? This 0 here cannot be a test point. No, because resolution is always greater than 0. So 400 times the resolution is going to be some number, and your resolution is never going to be 0. So example of not following the standard. So if we look here, we see this 0, we see 500. Our first force point, non-zero force point, is 500. The Class A lower limit here is shown at 192.3. This certificate violates the E74 standard right there. And look at it up close. Lower limit factor 0.48. Good lower limit factor, 192 on a 10,000 pound load cell, 192.3. But in actuality, the end user can only use this cell from 500 pounds to 10,000 pounds. If they're using it under it, they're in violation of the standard. Do not assign a Class A or Class AA verified range of forces below the first non-zero force point. We have observed numerous labs violating this rule. And why? Because it's easy. You can use, typically they'll use one standard and they won't have to change out standards. Changing out standards costs money, costs time. They would have to charge more. If you're sending to these labs, my advice is demand that they do a 2% force point. Tell them, make them change out their standards, make them follow the ASTM guidelines in section 8.6.2 and 7.2.1. Calibration in accordance with ASTM E74, and again, secondary force standard, an instrument or mechanism, the calibration of which has been established by primary. So here's an interesting example. So if we look at this, may not see it yet, what's going on. We look at this, hey, guess what? Class AA, this particular certificate, they assigned a Class AA loading range. Interesting. So they use primary standards, right? Nope. They used an Interface gold load cell. Interface makes great gold load cells. 1620 AJH to 25K. Know that cell. Great load cell. However, it's not good enough to assign a Class AA loading range. Only calibration with primary standards can assign the AA loading range. So calibration lab is using a load cell to this completely breaks the standard. Then someone else assigns a Class AA. Again, it's that confined TAR, and if you're breaking that, you're completely breaking the standards, and nothing. All these calibration that you do after that is going to be absolutely worthless. So do not assign a Class AA verified range of forces unless you are calibrated with primary standards accurate to better than 50 parts per million. Do not assign a Class A verified range of forces unless you are calibrating the device using the secondary standard that was calibrated directly by primary standards. A force measuring instrument with a Class A verified range of forces cannot assign a Class A verified range of forces. And guess what? A force measuring instrument with a Class AA verified range of forces cannot assign a Class AA verified range of forces. So we get to the actual calibration procedure. We're looking at the deviations from the fitted curve. We're basically going to run. We're going to run our force applied. We're going to run all our numbers here. and we're gonna curve fit these, and then we're gonna take the deviations, all these numbers here from the fitted curve, and we're gonna run them through this equation. And if you notice, what's interesting is n minus m minus 1. Well, n, sample, so we have 33 minus m, the degree fit. Here we have a third degree minus 1. In standard statistics, you normally have the n minus 1. ASTM adds the n minus m minus 1. That makes that divisor a bit smaller and errs on the conservative size. So calibration equation, deflection or response, and then LLF is 2.4 times the standard deviation. So we get a standard deviation converted to resolution multiplied by 2.4, we get our LLF, and the class A range is 400 times the LLF, class AA range is 2000 times the LLF. ASTM does allow substitution of electronic instruments. The indicating device used in the original calibration and device to be substituted shall have been calibrated and the measurement uncertainty determined. This is a pain in the butt. Some people want to do it. The uncertainty of each device shall be less than 1/3 of the uncertainty for the force measuring system. Look, with indicators as cheap as they are right now, I'm telling you, I often, if I advise people, I say, look, why not pair each load cell you have with its own indicator? If something happens, you only have to have one thing recalibrated. If you want to pair, 4 or 5 load cells to one system and that system goes down and you want to substitute, you can do it, but then you're going to be calibrating your indicator every time it goes out for cal and calibrating the other indicator. You're going to have a simulator. You're going to have to purchase more equipment. It's more work. Some people do it. They think it's an insurance policy. Others say it's not worth it. So if you do substitute, you should substitute the exact same meter, the same excitation amplitude, waveform, and frequency, and ASTM says they shall be maintained. And then it says cable substitution should be verified with a transducer simulator. It's great that it has that, and it says should be, and it's hard to do that because most simulators do not have the same wiring or connection as the actual load cell. So that can be problematic and hard to do. This section is under a rewrite. I imagine it's going to change within the next revision of the standard. So if we summarize the cal procedure here, we allow the UUT to come to room temperature. Warm up instrumentation, remember 15 to 30 minutes electrical, select 10 to 11 force points. Remember that first force, you're not going to be able to use the device below that first calibrated force point under any situation. Fix the UUT in the test frame, exercise 2 to 4 times, apply the first series of forces, run 1, rotate 120 degrees for run 2. I said if possible. If you're doing a proving ring, you can rotate 60 or 300 for run 2. Apply the second series of forces, run 2. If the UUT is compression and tension, switch to the other mode after finishing run 2 and exercise and repeat the steps above. When we do this, we can do tension. If we start in compression, we can do run 1, run 2, go to tension, do the full cal, come back, and then rotate another 120 degrees for run 3 and finish it. Apply the third series of forces, run 3. Okay, so we get a calibration, or a customer says, hey, I need something calibrated in accordance with ISO 7500. And the person has, maybe Morehouse has done the calibration on the equipment, and we've done it to ASTM E74. Well, the problem here is, and the person should not commit to doing the ISO 7500-1 calibration with an E74 because ASTM E74 is not the same as ISO 376. We have a paper that you can look at in CalLab on this, and we have several blogs. So ISO 7500 is the European equivalent for calibration and verification of static uniaxial testing machines and requires standards to be calibrated in accordance with ISO 376. You just simply cannot use ASTM E74 for ISO 376, and ISO 376 has several requirements that are not requirements of E74. So E74, repeatability with rotation, that's great. That's an E74. But these other ones, repeatability without rotation, not. Fit error, not. Resolution, not. Machine uncertainty, ISO does a great job of classifying the machine. So if my reference is only good to 0.2%, I cannot assign a class 00 range. Luckily, this one was done in dead weight. Also, we have 0 error. And if it has ISO 376 requires reversibility, and if you don't do reversibility, then it can do ascending only for per case 3, and you can do a creep test. And here we give the combined expanded uncertainty. So again, here's the table. Here's for the standard that I was talking about. If my standard's only good to 02, I can only assign a class half range. If my standard's good to 05, guess what? I can only assign 05 or better, I can only assign class 1. I cannot assign class half or class 00. So again, 376 tests for all of these errors. It's either reversibility or creep, depending on the case C or case D. So ASTM is not ISO 376. ASTM requires standards to be calibrating in accordance with the E4 requires calibration in accordance with E74. 7500, ISO 7500 requires calibration in accordance with ISO 376. The ASTM E74 procedure calculates a lower limit factor based on a series of measurements in which the standard deviation from the predicted response is calculated. It's fairly simple. So there's an example of ASTM, standard deviation, resolution, lower horse unit, 50 pounds. Guess what? 50's here because that was the first force point that applied to 2000. You know, if you multiply 0.037 by 400, it could be less than 50, but 50 was the first point that was applied. ASTM has an interesting note that deals with alignment. It says force measuring instruments have sensitivity in varied degrees depending on the design, mounting conditions, and parasitic forces and moments due to misalignment. A measure of this sensitivity may be made by imposing conditions to simulate these factors, such as using fixtures without contact surfaces that are slightly convex or concave or of varying stiffness or hardness, or angular or eccentric misalignment, and so forth. Such factors can be significant contributors to measurement uncertainty and should be reflected in comprehensive measurement uncertainty analysis. Basically, we're talking about different adapters and the effect they have on load cells, and keeping the line of force pure, free from eccentric forces, is the key to calibration. As you can see here, the green line is the main loading axis. This orange line, if this is the actual load line that we apply during calibration, this difference is really our eccentric force. And there are numerous adapters and things that can be used that make a huge difference. Here is one with a Sensitech model RFG F22601 load cell. I did a test here. I used this adapter, really simple, with 1.5 inch engagement, an adapter with just 1/2 inch engagement, put 10,000 pounds on it after I exercised it, and observed readings of 10,000 and 1.5 and 9,942.3. Now this customer did not send a top adapter with it, and we notified them what was going on. They said, just noted on the cert, we noted that we engaged the load cell to 1.5 inches. But so you send this load cell into another calibration provider, what do? They just calibrate it and give it back? What if they're using 1 inch and you're using 1.5 inches? What if they're using 1/2 inch and you're using 1.5 inches? All of a sudden, a device where you're expecting it to be good to 0.25 is 59.2 pounds out. It's just silly. Different hardness of top adapters. We see this one a lot. Here's one where we did some rotational tests as well. We used a 4340 top block, and then we used a hardened top block. The interesting is the difference, 0.3%. So 0.3% is 12 times the 0.25 as allowed by the standard for a Class A device. If the lab is claiming 0.013% uncertainty and not sending their top adapters, there's serious concern. Look, if they're just sending a load cell in and then they're using that as a standard and they're doing their CMC and saying, hey, yeah, great. Chances are they're not doing their proficiency testing right, because they would catch it, or they don't have a good proficiency test artifact. And the other thing is, they're going to be way off. 0.3% right there, 0.13, it's just not going to happen. So the recommendation is to use, have top and bottom adapters if possible, and alignment is the key. That first example in compression using a ball adapter pictured right, if the machine has a ball adapter, often yields the best results. If a ball adapter does not exist, a spherical alignment adapter pictured left will help. So in that first scenario with the Sensitech cell, if we would have used something like this, the customer would have sent it in, we would have repeated all day long. They didn't, so the cell has different thread depth. And then we talked about the hardness of top blocks. Here's a picture of our concrete kit. This is for E4 testing, calibration in accordance with E74, 600K cell, a 60K cell, and a 5K load cell. Here's the top blocks for all the cell, bottom base plate, one bottom base plate that can be used for all 3 of these load cells, because you're never going to use them at different times, most likely. Top adapters and a top adapter, a hardened top adapter for the 600K. This 600K, we set a concrete set, and I'd stress that because this cell was designed specifically for transport. This cell right here, it weighs about 25 pounds, and with the top and bottom adapter weighs less than 40 pounds. This whole kit can ship at less than like 65 pounds. It can be shipped in two cases that can easily be carried on airplane on location. Real simple to set up and do concrete machines. And you have the wrong tension adapters. If any of any of your adapters look like these tension adapters in your lab, there is a problem. Even straight threaded rod can introduce misalignment issues, as they can distort the line of force in non-Morehouse machines. They can distort the line of force in Morehouse machines. Our machines, we're using that ball adapter typically in the top when we mount the reference, so that our machines are a little more forgiving than others, but in general, they're not good practice. Any machine misalignment of 0.01 degrees can affect the reproducibility of some load cells. Even our spherical adapters can only overcome about 0.1 degree of misalignment. So really important. And I say our spherical adapters, here's an example of them over here in the machine with the load cell. Tension member adapter, we can adapt a bunch of different things, clevises, tension members to load cells, various things. This is a quick change adapter fitted with 2 ball nuts and 2 ball cups. Here's the design characteristics here and the actual adapters. And then if you look at the tensile force cal, we have the basic ones. Then we have our TMA sets here for various load cells. And then if you have dynamometers, ED2000s, other ones, Tractel, Dillon, all those, there's pin size requirements. Not calibrating with the proper pin size can produce errors 17 to 20 times the actual tolerance of the device. So all these are mated with the right pins, the right shoulders, the right strength. They have at least a 2-to-1 safety factor on all of them, and there's a chart that if you want to calibrate a Dillon ED 25K, ED2000 25K, it'll tell you exactly which pin size you need and what part number to go pull and fix everything up. Really just a simplistic set to ensure you're meeting the manufacturer's recommendation, and that you're not pulling with a pin size that's too large or too small, so you can replicate what needs to be done so the end user can repeat the results. So, and then we talk about competency and measurement error. Some examples of competency, and we discuss this. Using proper adapters when calibrating force instruments. Improper adapters can produce errors 10 to 20 times that of manufacturer stated accuracy. Proper alignment of the UT unit under test, adapters, and proper methods for loading threads. Other error sources, some discussed, some not. Misalignment, different hardness of adapters, thread loading versus shoulder loading. They all contribute to a decrease in the repeatability of measurement results, resulting in additional measurement error. Repeatability and reproducibility tests, as well as proficiency tests, are good methods for detecting measurement errors. So I'd like to thank everybody for your attendance. Your time is valuable. If you're not already a member, I'd encourage you to sign up for our free Force Measurement Insider, where if you want free reviews of calibration certificates from other force calibration suppliers, we will tell you what's wrong with them, if there is anything wrong with them. If you want to use us for calibration or are not sure that we can meet your needs, I'd offer to perform a calibration, send you the data, and you only pay if we meet your needs. Exclusive Excel templates, so you're accredited, you want to get accredited to the new 17025 2017. We have PFA calculators for method 5 and method 6, ANSI, NCSLI, ANSI, Z540.3 method 5, method 6. We have sheets, Excel sheets for that. We have Excel sheets for uncertainty. We have all kinds of things that we like to give and help our customers whenever possible. You also get access to upcoming information, upcoming webinars, training, free merchandise, customized online training for your company in regards to force or torque. You have 3-4 people and you want an ASTM webinar with an open mic, or you want a webinar on measurement errors, happy to have an open mic, open phone conversation where we just go over everything one by one. Open Q&A forum. Then again, articles on force torque, our latest papers, everything else. Exclusive offers on force calibration equipment and training, and time-saving tips using lean manufacturing. So hopefully at the end of it, at least these time-saving tips, the right adapters, everything else, you can actually start to have a very good return on investment if you start employing and using some of these things. So again, if you have the PDF, I encourage you to sign up. And if not, I take questions and thank everybody for their time.